Hello and welcome back to the channel. I'm excited to share with you one of the most powerful applications transforming how we discover content online: AI-powered recommendation engines using vector databases. Whether you're scrolling through Netflix, shopping on Amazon, or listening to Spotify, you're experiencing the magic of these systems every single day. In today's deep dive, we'll uncover the technology behind these intelligent systems. You'll learn what recommendation engines really are, how AI vector embeddings make them incredibly smart, why vector databases are the secret sauce for lightning-fast results, and I'll even show you how to build your own recommendation system with actual code. So grab your favorite beverage, hit that like button if you're ready to learn something amazing, and let's dive into the fascinating world of AI recommendations. Let's start with the basics. A recommendation engine is like having a super intelligent personal assistant that knows your preferences better than you do sometimes. These systems analyze massive amounts of data about user behavior, preferences, and content attributes to suggest exactly what you might want next. You encounter these systems everywhere. Amazon suggests products based on your browsing history and purchases. Netflix recommends movies using your viewing patterns and ratings. Spotify creates personalized playlists by understanding your music taste. YouTube's algorithm decides which videos appear in your feed. Now, traditional recommendation methods like collaborative filtering, which suggests items based on similar users, and content-based filtering, which recommends similar items, work okay for simple scenarios, but they struggle with what we call the cold start problem. Imagine you're a brand new Netflix user. How can the system recommend movies when it knows nothing about your preferences? Or what about recommending a newly released product that no one has purchased yet? This is where AI and vector databases become game changers. Here's where things get really exciting. Modern AI models, think BERT, GPT, or advanced neural networks, can convert any type of content into what we call vector embeddings. These are dense, numerical representations that capture the deep, semantic meaning of data. Instead of simple keyword matching like action movie equals action movie, vectors understand that thrilling adventure and high-octane drama are semantically related. The AI captures subtle relationships, mood, style, and even abstract concepts that traditional systems miss completely. Picture this. Every movie, song, product, or piece of content exists as a point in a multi-dimensional space. Similar items naturally cluster together. A romantic comedy might be close to other rom-coms, but also near feel-good dramas and lighthearted movies. With just these few lines of code, we've transformed product descriptions into mathematical representations that capture their essence. These embeddings become the foundation for incredibly intelligent recommendations. Now, you might be thinking, why can't we just use regular databases? Here's the challenge. Traditional databases are designed for exact matches. They're great at finding customers named John Smith or products priced under $50, but they can't efficiently find items similar to this vector. Vector databases are specifically engineered for similarity search in high-dimensional spaces. They use sophisticated algorithms like HNS-W, hierarchical navigable small world graphs, or IVF, inverted file indexes, to find approximate nearest neighbors incredibly fast. We're talking about searching through millions or even billions of vectors in milliseconds. A traditional approach might take hours to compare vectors one by one, but vector databases do this in under 100 milliseconds. These databases support different similarity metrics depending on your use case. Cosine similarity measures the angle between vectors, perfect for text and content similarity. Euclidean distance measures actual spatial distance, great for numerical features. Dot product captures magnitude and direction, useful for user preference scoring. Let's look at how everything fits together in a production recommendation system. The architecture has four main components that work in perfect harmony. First, we have the embedding generation layer. AI models continuously process user behavior, item descriptions, images, and metadata, converting everything into vector representations. Think of this as the brain that understands content at a semantic level. Second, these vectors are indexed in the vector database using optimized data structures. The database creates smart shortcuts and clusters that make searching incredibly fast, even with billions of vectors. Third, when a user needs recommendations, their profile vector is searched against the entire index. The system finds the closest matching item vectors in real time. These become the recommendation candidates. Finally, business logic and filters add the finishing touches. Maybe you want to exclude items the user already owns, boost newer products, or ensure diversity in recommendations. This layer handles all those real-world constraints. This architecture scales beautifully. Whether you have thousands or millions of users, the core similarity search remains lightning fast. The applications of vector-based recommendations are virtually limitless. Let me show you some fascinating real-world implementations that might surprise you. In e-commerce, companies like Amazon use vectors to understand product relationships beyond simple categories. They can recommend complementary items, seasonal alternatives, or products that match your style preferences even if you've never searched for them specifically. Streaming platforms take this even further. They analyze not just what you watch, but when you pause, rewind, or skip content. They consider audio features, visual styles, director preferences, and even the time of day you typically watch different genres. Social media platforms use vector embeddings to understand content semantics. They can identify that a post about machine learning might interest someone who engages with artificial intelligence content, even if the exact keywords don't match. In healthcare, which might be surprising, vector databases help match patients with similar medical profiles to suggest treatment options, clinical trials, or relevant research papers. This is revolutionizing personalized medicine. Gaming companies use vectors for player matching, ensuring you're paired with others of similar skill levels and play styles. They also recommend in-game items, characters, or content based on your gameplay patterns. Let's talk about why vector-based recommendations are so much more powerful than traditional approaches. The advantages are truly game-changing. First, semantic matching. Instead of relying on exact keyword matches or simple collaborative filtering, vector systems understand meaning. A search for cozy mystery novels can surface books described as quaint detective stories or charming whodunits because the vectors capture semantic similarity. Second, they solve the cold start problem elegantly. Remember our new Netflix user? With vectors, the system can analyze the content itself, genre, mood, actors, directors, and make intelligent recommendations even for brand new users or items. Third, the scalability and speed are incredible. These systems handle millions of items and users while maintaining sub-second response times. The approximate nearest neighbor algorithms are so efficient that adding more data doesn't significantly slow down the system. Fourth, cross-modal recommendations open up entirely new possibilities. You can recommend products based on images you liked, suggest music based on the mood of articles you read, or find movies that match the aesthetic of photos you've saved. Now, let's be realistic about the challenges. Building production-ready vector recommendation systems isn't without its complexities. The biggest challenge is embedding quality. The old programming principle, garbage in, garbage out, applies here more than ever. Poor quality embeddings will lead to irrelevant recommendations, no matter how sophisticated your vector database is. There's also the eternal trade-off between speed, accuracy, and scalability. Approximate nearest neighbor algorithms are fast, but might miss some relevant results. Exact search is accurate, but too slow for real-time applications. Finding the sweet spot requires careful tuning. Real-time updates present another challenge. User preferences change constantly. New items are added regularly, and your embeddings need to stay current. This requires sophisticated data pipelines and careful consideration of when and how to update your vectors. Bias and diversity are crucial considerations. AI models can inadvertently reinforce biases present in training data. If your recommendation system only suggests mainstream content, users might miss discovering amazing niche products or diverse perspectives. Finally, there's the explainability challenge. Traditional recommendation systems can easily explain why they made a suggestion. Users who bought this also bought that. Vector-based systems are more of a black box, making it harder to explain recommendations to users or debug problems. All right, let's get our hands dirty and build a recommendation system from scratch. I'll walk you through each step with actual code you can run. Step 1 is generating embeddings for your data. For this demo, we'll use sentence transformers, which is perfect for getting started quickly with high-quality embeddings. Step 2 is choosing and setting up your vector database. For this demo, we'll use Pinecone, but you could also use Milvus, Weaviate, or Chroma, depending on your needs. Step 3 is indexing your vectors with metadata. The metadata allows you to add filters and additional context to your recommendations. Step 4 is implementing the search functionality. This is where the magic happens. We convert user preferences into vectors and find similar items. Now, let's add some production-ready features that will make your recommendation system truly professional. First, let's add A/B testing capabilities to continuously improve your recommendations. Second, implement feedback loops to learn from user interactions and continuously improve recommendations. Third, add sophisticated filtering and business rule capabilities. Finally, let's talk about monitoring your recommendation system in production. These metrics will help you understand performance and identify areas for improvement. Let's wrap up everything we've covered today. AI-powered recommendation engines using vector databases represent a massive leap forward from traditional recommendation systems. We've seen how vector embeddings capture semantic meaning in ways that simple keyword matching never could. We've explored how vector databases enable lightning-fast similarity search at massive scale. And we've built a complete working system from scratch. The future of recommendations is incredibly exciting. We're moving towards systems that understand multimodal content, learn from implicit feedback in real time, and provide personalized experiences that feel almost magical. If you found this deep dive valuable, smash that like button and subscribe for more AI and machine learning content. I'd love to hear about your own recommendation system projects in the comments below. Thanks for watching, and I'll see you in the next video. Keep building amazing AI systems.